I continue. That leads to excessive optimism about future growth of earnings, which is what we call long-term growth or LTG, that inflates valuations, the price-dividend ratio. It leads to disappointment and to low returns. And what we're going to try to do ultimately is to, in fact, link the disappointment or the level of disappointment to stock market returns. So we'll use expectations to actually trace very detailed implications of this theory. Okay, let me skip this. So I'm going to talk about expectations, then I'll briefly talk about excess volatility, and then I'm going to talk about return predictability. I'm not going to go. You have to trust that Rafael Laporte is a co-author of this paper, so everything is kosher in the data. So let me first explain to you the data on expectations, and do expectations move too much? So in the last 5 years, both finance and macroeconomics have adopted this idea from Koibion and Gorodnichenko's work on testing models of rational expectations. And what rational expectations predict is that if you have a forecast and you have a forecast error, that it can't be predicted from anything at the time the forecast is made. In particular, it cannot be predicted from the revision of the forecast at the time the forecast is made. So if I revise a forecast upward today, it shouldn't be able to predict my forecast error in the future. But the idea goes further, which is, suppose I revise my forecast upward today, and suppose systematically my forecast ends up being higher than the realization of the variable I'm forecasting. Well, we can call it overreaction. And that will correspond in this regression to the negative coefficient of the regression of forecast error on forecast revision. And conversely, if we find a positive coefficient, that means that forecast was not revised enough, and so that realization is going to be above the forecast. So this whole methodology has proved just enormously productive for doing macroeconomics. Now, this is what you do when you regress this with earnings, with corporate earnings for the whole S&P 500 index. What you find is, if you regress forecast errors and forecast revisions, at short horizons of, let's say, 1 or 2 years, you don't find much. But if you look at this variable called LTG, which is long-term growth forecast, you find very strong and negative statistically significant coefficients, which says that if you have good news, then analysts' forecast of long-term growth of fundamentals, long-term growth of earnings, systematically exceed the realization. And what we'll show is that actually this explains many of the puzzles. In fact, here is what the data look like. Suppose you have here at S equals to 0, a positive shock to earnings growth of the corporate sector of S&P. This is what actually happens in the true data, which is to say analysts understand if you have a positive earnings forecast, it's going to mean revert, earnings growth realization is going to mean revert in the short run, but then it's going to recover. But what you see in the data is that in their forecast, analysts are too optimistic, which is that they underestimate the extent of the reversion. But more importantly, for understanding long-term volatility of stock prices, they are way too optimistic in the long run in response to a positive shock, which is to say that the red line is of expectations is higher than the green line of the truth. So you get underreaction, you don't go down too far enough in the short run, and overreaction in the long run. Now, one other feature of expectations is that these forecast errors and forecast revisions are highly predictable from past growth of fundamentals. So here we're regressing forecast revisions on past changes in earnings. over the previous 5 years. And what you find is that, as I showed you in the previous picture, if you have very fast growth in earnings, in the short run, forecast revisions recognize that this earning growth will not continue. But in the long run, you have a large positive coefficient, which is to say that there is a sharp revision of long-term earnings growth forecasts. And in fact, you can do this as a two-stage least square regression where you forecast the, where you predict the forecast revision, and you find that the predicted component of forecast revision predicts the forecast error. In other words, it's very direct evidence of extrapolation. So this is what you get out of expectations data. The question is, they're forward-looking, but not rational. They're too optimistic in the long run about the fundamentals. So can we measured beliefs account for stock price puzzles? Well, what do? I'm again going to only show you small pieces of it. The first is excess volatility. So we're going to plug in this forecasts, well, always stands for observed as opposed to rational expectations, of earnings growth into the present value formula, again, under the assumption that discount rates are constant, so we're not doing anything with discount rates. We plug that in, and this is the first result we get, which is, this is the variance of actual prices, is 15.2% standard deviation. The second column is the standard deviation of rational expectations prices as computed by Schiller. See, it's almost zero. And the third line is the rational expectations of values, the valuation of S&P 500 using actual forecasts to compute the present value of expected dividends. And you find that you get something very close to the data. In other words, expectations of dividend growth actually do a very good job for explaining stock prices. But it's not just you explain the volatility, you actually explain the whole path and the levels. This is the figure I've shown you earlier, which is that once you use the technology I've described to you, you get the prices to follow pretty closely the actual observed stock market prices. Let me skip price dividend variation because it's too financy, but you get the result that in fact the variations in the price dividend ratio actually account, I explained, by this forecast as well. But what I want to show you is, you know, the last piece is that actually the model works, which is that there is a link from strong growth to excess optimism about long-term earnings growth, to inflation of the price dividend ratio, to predictable disappointment, which is to say expectations get revised downwards, and predictably low returns. As an aside, by the way, because the data looks so good, the obvious objection is, well, maybe the way in which analysts present LTG is that they look at stock prices and they ask the question, what is the forecast of long-term growth of dividends that would account for these prices? So maybe we're just observing an accounting relationship. And there is a fair amount of work in the paper I don't have time to go through that says that this is not the case. Okay, so this is the final piece of the evidence, which is what we've been working for, is that suppose you're trying to predict returns, you know, over the 1 year, 3 years, and 5 years, so those are the 3 columns, and with different forecasts. And what you find is that LTG, which is the forecast that we have observed, the forecast of long-term dividend growth actually does predict returns with a negative coefficient. which is to say when forecasts are extremely optimistic, that they're excessively optimistic, and stock returns.
Andrei, you have about 5 minutes.
Yeah, I'm doing great. Well, I'm not sure I'm doing great intellectually. I'm doing great on time. Short-term earnings growth forecasts, in contrast, don't do anything. But what about the link? Can we actually trace out in the data the link from fundamental news to belief revisions to return predictability? So we're going to start from forecast revisions that are predicted from proxies for fundamental news, such as past growth of earnings. So we're going to conduct two tests. We're going to regress returns on predicted revisions, which is to say, if earnings growth has been high, and I can predict that LTG is going to be revised upwards, can I also predict low returns going forward? And the second test, which is even maybe somewhat subtler, is we regress returns on forecast errors entailed by the predicted revision. So I have a predicted revision. Which leads to a forecast. That forecast leads to an error. For example, if I'm too optimistic, there's going to be a positive error. The forecast is higher than the realization. And the question is, and there is also going to be a low return because people are disappointed. The question is, can we connect the forecast error to the return, or the predicted forecast error to the return? Because that's really a strong test of people being excessively optimistic, disappointed, which leads to low returns. So these are the results of the first test. Again, on the columns here are the regressions. So we're looking at the return between years t and t+2 or t+5. The independent variables in the first two rows are forecast of short-term earnings, which don't work. But the last row, which is in the box, is the predicted change in long-term growth rate of earnings. And again, we use past growth rate of earnings as an instrument. And what again you find is then when we can predict that the earnings forecast is going to go up, we can also predict low returns going forward. In other words, the bigger the predicted revision of earnings growth, the worse are the returns going forward, which is to say the market does overreact to news. And so this is the final graph, which is we're looking at predicting returns from errors in the forecast. We're looking at predicted forecast revision. And again, you find a positive coefficient, which is to say that when you're going to get realization below the predicted forecast, the predicted forecast, those are the times when you're going to see low returns realized in the marketplace. So again, this piece also lines up with the prediction of this informal theory. So just to summarize, to take stocks, we provide some support for a model in which you say strong growth of fundamentals leads to excessive optimism about long-term growth, inflated valuations, future disappointment, and lower returns. You don't get anywhere near the same significance of the results with the expectations of short-term growth, which underreact, but they don't lead to, don't explain any return predictability. Okay, so finally, let me just conclude. It looks like, I mean, you know, we don't have a final model, although we have some pretty clear evidence of the mechanism. But it looks like Shleifer and other puzzles have a pretty straightforward resolution. The resolution has nothing to do with the changing discount rates or volatility of discount rates, which is the path that finance has taken over the last 20 or 25 years. But the evidence seems to line up very strongly with a model of extrapolation of fundamentals, particularly long-term growth. And we've described the mechanism, which is to say that there is overreaction to fundamental news that drives prices and return reversals as errors are corrected. Thank you very much. I have some backup slides if this come up. But
Thank you, Andrei. So, when, Jessica, are you ready to take over?
Yes. Thank you so much for including me. This is joint work with Michael Kahana. Okay, so the broad motivation is the really common approach in economics since rational expectations are really before, is that all agents start with a probability space and they assign probabilities to the events in the probability space, not just to next period, but essentially all the events forward in your lifetime. And if you think about that, that's pretty unrealistic. It's hard to think about most actual problems that way. So we start with the idea that when facing some decision under uncertainty, instead of thinking about a lottery, so the lottery being basically the savage models that we're all facing lotteries all the time, compound lotteries, we're instead going to draw from our memories and perhaps play out scenarios, but the strength of the scenario will come from the memory. So this paper is an implementation of that idea. Now we're going to address 3 problems, or in this talk, I'm going to focus on 3 problems, and the paper is a little bit more about underreaction, overreaction. So the first one is going to be evidence on the role of experience in decision-making, and I've cited a couple of really strong results by Malmendi and Nagel. There's a large literature on this that experience matters and has permanent effects. I'm going to talk about an application to the financial crisis and to rare events in general. So we've all had, one of those being the pandemic and the lockdown, and it seemed so unanticipated, and yet, as we all now know, there was a previous pandemic. So we can, think about why all of a sudden this event, which really was part of, should have been part of in the information set for many people, was not. And then finally, the evidence that external stimuli affect decisions in ways that they shouldn't. So I'm going to focus on applications to those 3 problems. Okay. So the framework I'm going to be using is retrieved context theory, and building off some really basic, long-known facts about memory. The memory system maintains a record of associations between features and an internal context. And the point is that the features that are present in the environment cue the context, and that tells the agent what information is most relevant. So it's actually a very optimal, smoothly operating process, but sometimes we can notice when things go wrong. And then dating back to Aristotle are the classic laws of association, such as recency, better memory for recently experienced items, semantic proximity, better memories for items that have similar meaning, and temporal contiguity. And this last piece is really what distinguishes this internal context model from other models. Better memory for items experienced close in time to a just remembered items. And sometimes this goes by a more evocative term, the jump back in time. Okay, so we use the temporal context model, which Mike's developed in other work for many years. And here's how it works. There's features of the environment. Those are just the observables. There's going to be a completely endogenous context state C. That's a latent state. And as I said, it will be endogenous. There's going to be an initial set of associations. And then over time, the agent's going to build on these associations. Okay, so, how does this actually work? So just imagine a whole bunch of features vectors. So these are vectors in an enormous dimension, space of enormous dimensionality. But we're going to think about small dimensionality here in this model. Context is going to be a vector too. And then here's a key point is that context evolves autoregressively. It depends on past context. And then it depends on retrieved context, and zeta is the weight on retrieved context. So CT in for input, is retrieved context. Okay, so that's features and context. Now, where does this retrieved context come from? Well, it comes from the agent's association. So it comes through this memory matrix, we'll call it MT. And the observations that the agent sees get filtered through MT. So what you do is you take the feature vector, you multiply it by the memory matrix, and out comes your context. Now, of course, where does memory come from? Well, memory comes from past context and features that get associated together. And the way they get associated is through an outer product. And just because outer products are somewhat unfamiliar, I just gave a little example here. So if you take context and then you multiply it by features transposed, that gives you something of the same dimensionality as memory. And what happens is you store the context in with the features. So it's like you're basically storing a bit of data in your memory. And that's basically it. Now, what's some intuition for this? Okay, so what happens when you see features F? Well, so this is the magic of this outer product. Okay, so F comes in, it multiplies memory. Then what you're doing is you take an inner product of those features and all the other features you've ever experienced. And the idea is that this is what your brain is doing, the hippocampus actually, or potentially something else if your hippocampus is damaged. Anyway, so the brain is taking all these features vectors, multiplying together. And the point is, if the dot product, if the similarity of the features are 0, you get zeroed out. If the similarity is high, then you retrieve that context. So the point is, you retrieve the context that you experienced under features that are similar to the present features. So, for example, you know, it's a little tough when we're all in, you know, in this situation. So we haven't been visiting New York. If we were visiting New York, we retrieve other contexts of having been in New York, for instance. But let's say you go back to your house after having been there, not having been there for a long time. So the features are your home, where you say you haven't been, your previous home where you haven't been for 20 years. And all of a sudden you might remember many things that you've never remembered before. So if you go back to this home, you haven't seen it for 20 years, that retrieves a context, and then context itself will retrieve other features. So first of all, you can think about context first as shining a light on what's going on now. That's CT-1. That's the most recent things that are happening. And then retrieved context can go way back in time. And this is the dramatic thing about this model, is that you can remember things that you never thought you might remember because of retrieved context. Now, I mentioned that there's this additional step, and that's retrieved features. So you retrieve a context, who cares? What does context do? The key piece about context is that it in turn retrieves a set of features. And I'm not going to go through the mathematical details here. It works in exactly the same way. The point is you retrieve the features that were experienced under similar contexts. And those are retrieved features. And that in this model is what gives you the probability distribution. So no longer do you necessarily have to think consciously about a lottery with probabilities. Instead, your brain just does it automatically, and the probabilities come out of these retrieved features. Okay, so there's a lot of support for this model in the memory laboratory. So how do you go from memory to decision making? So here we need a decision maker. And we're gonna basically map what comes to mind, the features, into the probabilities, as I described. Okay, so briefly, without getting into too much formalism, I'm gonna talk about what the economic setting is. And the most important aspect of the economic setting is there's a decision maker making a decision, choosing something. I'm gonna call it pie for portfolio, because as a financial economist, I think about portfolio choice. So basically you're deciding how much money do you put in the stock market. So you're making that decision, and when you make that decision, you're going to think about what might happen in the future. Is the stock market going to go up, or is it going to go down? That's the future why. That's going to be a feature. And so what do you think about those future features? Well, that's going to be determined by your present context, and that's what I'm going to talk about. Okay, now there could be if there's a persistent unobserved state, what all of this will do is it will help make this process optimal, which is not something I'm going to talk about. That's potentially a different line of work, which, you know, I hope perhaps someday people will embark on if they find this interesting, or we'll see. Anyway, roadmap. Okay, so the first thing I'm going to talk about is this key property, temporal contiguity, and how that matters. And then I'm going to take that, I'm going to build on it. So the first problem is the persistence of memory. Building on temporal contiguity, how do you get persistence through this process called retrieval and re-encoding? Then building on that, I'm going to go to the financial crisis, and then if there's time, irrelevant stimuli. Okay. So I'm going to give an illustration of temporal contiguity first. Now, this is really illustrative. It's not an accurate description of the Great Depression, which after all, most of us don't remember. But the point about the Great Depression is people link the 1929 stock market crash to the Depression itself. And that's in a lot of literature. How did those links get established in the first place? That's what I'm interested in. So this is pretty stylized. But the point is to illustrate temporal contiguity. Now, so consider an agent in 1929. That agent just experienced the 1929 stock market crash. And we're going to call that, because I'm going to use the example of financial crisis through this talk, we'll call this F crisis, crisis features. Now, 1929 context might have all kinds of things in it. It doesn't matter. The point is, in memory, the 1929 context gets joined together with the crisis features, and memory evolves. Now, shortly thereafter, it was really like in 1932, but let's just say 1930. Shortly thereafter, there was a set of other features, unemployment, all the things that we associate with the Depression. So there's Depression features. Now, this is just terminology. The context that gets retrieved by the Depression features might be totally different from the 1929 context. That's retrieved context Depression. Now context evolves. C1930 combines 1929 and Depression, and then there's a new set of associations in memory. There's now 1930 and Depression. Now suppose we see another financial crisis similar to 1929, and this works especially well if there hasn't been anything that's happened in the meantime that's that much like 1929. What happens is through those inner products, this crisis will reinstate the 1929 context. Now you may say, who cares? Who cares about the 1929 context? So by reinstating the 1929 context, the features that the agent will remember is not just the crisis. They will remember the crisis in 1929, but they will also remember the Depression. And here is why. Remember, features retrieval brings to mind the features experienced under a similar context. Because context is autoregressive, 1930 context is similar to 1929 context. It's a weighted average of 1929 in Depression. Now, the Depression is experienced under 1930 context. Okay, so what happens here is you get the features that remind you of 1929, but because 1929 and 1930 they have to be similar, the features that get retrieved, so look, 1930 includes 1929. So if you think about what features, so now you're in the 1929 context and you're asking what features occur to you if you're in the 1929 context. Well, the features that occur to you in the 1929 context are those very features that are experienced when you were in this context. Well, one of them is Depression, because you were partially in this context when the Depression happened. So there it is. So the point is, if a crisis happens, you remember the Depression. Even they don't have to happen at the same point in time. And this works, as I said, especially well if these are unusual events. This is the essence of temporal contiguity, better memory for items experienced close in time to a just remembered item. And the point is that context retrieves a rich universe, not just a single memory. So in the rest of the talk, I'm going to use this idea. So this is a reason for why an agent might begin with a set of associations. Two unusual events experienced close in time, then form an association in the agent's mind. Now, you might say, if that association does not represent any kind of physical reality, won't agents learn the truth quickly? And maybe, but not necessarily. And that's what my next part is going to explain. So in the memory laboratory and recall task.
Pass me the yellow envelope from that side of the bed on the floor.
Sorry? Okay, I'm okay, I can keep talking, right? Hello, can people hear me?
Yes,
Okay.
everything
Yes,
well.
absolutely.
All right,
Jessica,
okay.
you have about 5 minutes. I just want to kind of,
Okay, okay.
thanks.
We'll get through this. Okay. Okay, so how do these associations become permanent? Okay, so here's an example to illustrate how that happens. So suppose the agent is solving a standard portfolio choice problem. There's a risky asset return that could be gains or loss. And then the agent fears, let's say, a depression. So the agent could be faced with unemployment. And let's say depression can only occur with loss. Now, the first point I want to make here is that if this were a Bayesian agent observing depressions, this agent would learn very quickly that depressions are rare. And so you wouldn't actually be able to explain much in terms of heterogeneity or disagreement or the portfolio choice data we see with a Bayesian agent, even if the agent has incorrect priors of a rare event. So that's what this graph shows. This shows the Bayesian posterior probability of depression. After 10 years of data, it's pretty low, and asset allocation is pretty high. Okay, what happens in this model? Now, suppose zeta equals 1, the general case is solved in the paper. Okay, so we have a features space. The feature space is our gain, loss, and depression. And in depression, you lose your job, and there's a stock market loss. There's prior associations, and here's the key point. The loss and the depression occur in the same context, and that's because of the temporal contiguity mechanism that I just showed you. Now, what prevents this agent from learning? Okay, so here's memory. Along comes a stock market gain, retrieved context is gain. Along comes a stock market loss, retrieved context is then the second element, which is kind of the mixed loss depression. Now, what are the features that get retrieved from gain? Just gain. What are the features that get retrieved from context associated with features loss? Well, losses make the agent think of both losses and depressions. And you actually really need this because actually, like, why should stock market losses be that severe? So the point is, if a loss occurs, the agent retrieves a context. In that context are both losses and depressions. And now when you store the event in memory, what you store is the retrieved context from loss, and you store the features that you retrieved. So it is as if your own thoughts become data here. So the retrieved features become the re-encoded features. And what this means is you've now cemented, you have one more observation in your memory that depressions and loss and stock market losses occur together. So you've thought about a depression, you've cemented that, and the depression becomes part of memory. In this example with zeta equals 1, this is a permanent effect. And you can never undo this. So this is a graph with a lot of lines on it. I already talked about the Bayesian case, this dotted line. I'm going to talk about neglected risk in a moment, a little bit. This solid line, posterior probability, is the agent who never changes their probability, zeta equals 1. And then zeta equals 0.35, which is actually what's observed, is something that we work out in the paper, and you just get very slow learning. And it's basically going to depend. So this is basically, you can think about this as an average effect. And so you can be kind of between here and here. So you get some learning, just not as same as in the Bayesian case. Okay, so I only have a few minutes. So I'm going to skip the nitty gritty here. So the setting is that, so I'm going to think about the financial crisis. And so it's similar to previously in that the agent fears a depression. I'm going to think about a whole bunch of identical log utility agents, thus abstracting from what could be an interesting set of heterogeneity issues right now. And just think about the equilibrium in this case when an agent behaves this way. Okay. So first of all, as Andrei pointed out in the last talk, the changes in the price dividend ratio are pretty hard to understand if you think about rational agents. So in this full information case, the price dividend ratio should be constant. The price dividend ratio is about future dividends, and you shouldn't be able to, in this full information case, you shouldn't be able to forecast it. Okay, but so how can you generate an effect where a crisis, a higher disaster probability a higher depression probability can become a lower price dividend ratio? Okay, so let's say you see a financial crisis. So here our features are normal, nothing's happening, financial crisis and depression. And just for the sake of argument, let's say the crisis has no particular effect on the agent except through the beliefs. Now the agent has a set of associations. Again, this is driven by temporal contiguity, that crisis and depression share a context. So what happens, the crisis comes in, you get a retrieved context, and then the depression features are retrieved. So P gets updated. And so here's a potential graph. Okay, so you start with neglected risk, which is a term in Andrei and Nicola's other works. You start with neglected risk. This agent has no idea that a depression is coming. Oops. Then there's basically some short-term underreaction because context takes time to evolve. Eventually, though, when we get here, there's overreaction, even relative to a Bayesian model where the agent has the same associations. So this is what Andrei was talking about. So I actually promise I didn't plan this, but so there's evidence that there is short-term underreaction followed by overshooting. And then the price-dividend ratio recovers, but to a permanently lower level because the agent has learned new associations. So just to summarize, neglected risk, initial underreaction. Because the agent cannot escape context, this really is a model of overreaction eventually. And then there's a permanent change in price behavior. Okay, so I think with that, I'm going to wrap up because I must be over time. Wait, I don't hear you. So I'm going to assume the answer is yes. Okay.
The answer is yes.
Okay, so just to conclude, our past experiences form a vast database, and our beliefs are inescapably, in the view of this paper, tied to context. And retrieved context is going to influence beliefs in ways that represent clear departures, and once associated, unusual features tend to remain associated. Thank you very much.
Okay, it's great to be asked to discuss these papers. These are two really exciting contributions to the behavioral finance literature. It's unfortunately going to be hard for me to do justice to them in the little time I have here. They're both long and complicated papers that discuss, they have many new ideas in them, and it also discuss a bunch of different applications in each paper, but I hope to try to put it a little bit in the context of a broader set of issues we're trying to understand, and to stimulate people to then go to these papers and dig more into the details. So I imagine that to many of you it's already familiar that understanding expectation formation is a crucial issue, not only in economics in general, but certainly for understanding asset prices in particular. The dominant paradigm of rational expectations assumes that people's probabilistic beliefs are formed by correct Bayesian conditioning on whatever information is available to them, say to investors, and it's taken as given that that information available to the investors should include all publicly observable information, perhaps additional sources of information as well. But as Andrei was discussing, there are a variety of observations stressed over several decades now that don't easily fit with that hypothesis in the area of asset pricing. And if one asks, well, what are the things that don't fit with the rational expectations hypothesis, one can divide it to some extent into two categories of types of tests. One would be relatively direct tests of Bayesian rationality using reported beliefs or reported forecasts, either in laboratory experiments or in surveys. And Andrei talked some about econometric tests of that kind in connection with earnings forecasts for the stock market. And then secondly, the kind of thing that Andrei's paper is more about is the idea that you can also have a more indirect kind of test of the rational expectations hypothesis, looking at the behavior of asset prices. To do that, you need some linking hypothesis that connects the asset prices to expectations. If you make the additional hypothesis that asset prices should be consistent with a required rate of return, which is in fact constant, so that people's subjectively expected rates of return have to be constant, then you can get strong predictions about the statistical behavior of asset prices that also lead to a lot of problems for the rational expectations hypothesis. In the paper with Bordalo and co-authors, they discuss in particular three well documented at this point anomalies about stock prices fitting with the rational expectations hypothesis under the hypothesis of the constant expected rate of return. One, as Andrei mentioned, the observation that stock prices are more volatile than realized fundamentals are. If prices are a rational forecast of future fundamentals, then the predictable part of fundamentals should be varying less than the actually realized fundamentals do. So prices should be less volatile. Instead, as Bob Schiller pointed out, they're more volatile. Secondly, if prices reflect a rational forecast of future dividends, then to the extent that prices vary relative to current dividends, that should have to be because future dividends are predictably different from current dividends, so there should be predictable variations in future dividend growth lining up with these variations in the price-dividend ratio. Instead, there is not much forecastability of future dividend growth using the price-dividend ratio. And then finally, the hypothesis should be that if subjectively expected rates of return are constant and furthermore those are rational expectations, then actual ex post returns should not be predictable using any information available to investors. Instead, there is predictable variation in stock returns. Notably, the price dividend ratio is an example of a variable that can be shown to predict future returns. What they show, and this is something Andrei didn't talk about in too much detail, they show in their paper that all three of those anomalies can be simultaneously reconciled with a particular kind of model in which the subjective expected returns of investors are different from rational expectations. And they have a discussion of what kind of time-varying biases in investors' expectations would be needed to explain these different puzzles, and they show that a particular kind of not terribly complicated model of biases in forecasts would, if correct, simultaneously explain all three of the anomalies. And the way this works is that they postulate a model of subjective expectations where the subjective expectations at some date t of future dividend growth g from t plus s to t plus s plus 1 would be equal to the rational expectation of that future dividend growth plus another term, this epsilon m, which is a bias term. They assume that this bias term is the same regardless of the forecast horizon. So for near and further in the future forecast horizons, that bias at a given point in time is the same. Furthermore, the bias term needs to exhibit persistent fluctuations, not just varying, but when it's high, it tends to be high for a while thereafter. And finally, the fluctuations in this bias term have to be correlated in a particular way with innovations in the dividend growth process itself. So this positive theta m coefficient is also necessary. If one hypothesizes evolution of the bias term, like the equation here on the slide, then it will, that kind of assumption about biased expectations will simultaneously explain all of these anomalies. For people following this literature, it's worth noting that there are important differences. There's some similarities of this hypothesis to the hypothesis of diagnostic expectations that the authors have proposed in some of their earlier work, but there are a couple of important respects in which it's different. Here, this bias term is assumed to be the same at all forecast horizons. The diagnostic expectations assumption allowed a bias term to exist and to be correlated with innovations in fundamentals, but it predicted that it should die out as you look further into the future at the same rate as rational forecasts are dying out. Secondly, the bias term fluctuations need to be persistent over time. In the diagnostic expectations models, they were instead uncorrelated over time. And so what the authors show is that modifying the assumptions in these directions better fit with these anomalies in the asset pricing literature. The other thing, and it's what Andrei mostly talked about, that's very exciting about the paper, is that they show not just that there's a particular hypothesis about biases that could explain these anomalies, but that surveys of analysts' expectations, in fact, corroborate the existence of patterns of systematic bias and expectations of very much the kind that would be needed, and that I've described on the previous slide, that would be needed to explain these anomalies. And I think that provides pretty compelling evidence that not just that there are biases and expectations, but the biased expectations seem to be a large part, and perhaps the main part, of what's going on with these pricing anomalies. A question that it leaves open is, how are we going to explain then the existence of systematic biases of this kind, that they exist and that they would persist over time as investors observe more data. And I think that the psychological mechanism that was drawn on in the previous work of the authors on diagnostic expectations doesn't seem to be enough to explain what's going on, because one needs a mechanism that will produce biases that are importantly different from diagnostic expectations. What I think I'd like to suggest the key to this might be is, in fact, expectations being based on imperfect memory. So suppose that we imagine, to simplify the learning problem, that we have an investor that knows the autocorrelation coefficients of the dividend growth process, but doesn't know the mean of this process and has to estimate the mean then from past observations. If that's the case, then the forecast, the optimal forecast based on this estimate for the investor at a given point in time, will indeed equal the rational expectation plus another term. And that other term, regardless of the forecast horizon, will be some multiple of the same thing, namely the current difference between the investor's subjective estimate of the mean at time t and the true mean. So that's a little more complicated than what was on the previous slide with that single epsilon mt term, but it would imply perfect correlation between those epsilon mt's at different horizons. Furthermore, these coefficients, lambda sub s, would ideally be different for different horizons, but importantly in this model, they would not die out for long horizons. Instead, they should converge to 1 for long horizons, and so become essentially the same non-zero value for all longer horizons. And so that's a lot like what was being postulated in the author's paper. So if one had imperfect estimates of the mean that had the property that subjective estimates of the mean fluctuate over time, furthermore, higher dividend growth makes the subjective estimate of the mean larger, and then thirdly, these fluctuations in the subjectively estimated mean are persistent, although not necessarily permanent, then this model will make predictions with the properties that the authors show will explain the 3 stock market anomalies. Should there be erroneous estimates of the mean like that, I think those are natural features of a model where investors' estimate of the mean have to be based on limited memory of past observations of dividend growth. There are various models in the recent literature that would suggest why people would have expectations like that based on limited data rather than a more complete data record. Malmendier and Nagel stress the role of personal experience being more accessible than other historical data sources. Nagel and Shu have an interesting recent model that proposes a modified Bayesian updating rule that incorporates fading memory. And in recent work of mine with Rava da Silveira and Yeji Sung, we propose a type of rational inattention model where there's endogenous memory precision. In that model, we show that with a cost of more precise memory that's increasing in mutual information, that you get the prediction of a memory state that's essentially an exponentially decay moving average of the past observations. So all of those models predict something relatively similar about the nature of imperfect estimates of mean dividend growth. They predict that it should be based on only some finite time window of recent observations, not the whole.
I hate to move it along, but we're a little bit.
No, I haven't given like 15 minutes yet.
No,
That's
you're
not
not
15
finished.
minutes. Oh,
No,
you
I
want
was-
me to go? You want me to move on? Okay. So I can
Continue.
explain everything that's in their paper, but anyway, I'll go on because I have a second paper to talk about. But I've said limited memory, I think, is the kind of explanation that the authors are looking for. And of course, the second paper by Jessica and Michael is indeed about positing boundedly rational memory processes as a source of departures from rational expectations model of asset pricing. This is another candidate model of limited memory that I think can explain the kind of puzzles I was just talking about, but it is a much richer model that in principle can explain other kinds of puzzling features as well. So they have a more general structure than the kind of learning model I was just describing, in which the role of memory is to allow the current situation to be associated with some hidden state that's thought to give rise to those observable features. The point of associating observable features with hidden states is that that's what's going to allow you to make forecasts in their setup. Future observables will depend on the future hidden state. The hidden state, though, is assumed to have some persistence over time. So identifying the current hidden state is the way you identify something that you can guess about the future, which will then allow you to forecast these future features. The role of memory is to keep track of associations between observed features and your conjectures about these hidden states, which is what the authors call context. And so it allows inference about the current hidden state from the features of the current situation. That's what Jessica was calling the model of retrieved context from the features of the current situation. Okay, it could be applied to the kind of model I was just talking about, where people need to estimate the mean of dividend growth. The hidden state would be that unknown mean of the dividend growth process, but it could also be applied to more complex cases like the ones that Jessica was talking about. How is their model different from just assuming Bayesian inference, but with a generative model that incorporates this idea of hidden states? I think there are two important ways that it's different. They're to some extent separable from each other, so I want to mention both of them. The authors have a model of how these conditional probabilities over the hidden states are formed from the current features. They don't assume, as in a standard Bayesian model, that those conditional probabilities are simply known because you know the generative model. Instead, they assume the conditional probabilities have to be learned from experience, and that's what the memory storage is in fact doing. But then secondly, given the retrieved context that's called to mind by the current situation, the perceived context and the forecasts that come from it involve another formula. They have a model of how the perceived context evolves over time and gets extrapolated into the future using a simple heuristic, which has the advantage of not requiring as much exact knowledge of the generative model parameters as a complete Bayesian updating rule would. Briefly, I have very little time, I think, to comment on these way they do this. I have some comments about them. Their model.
Keep going a little bit beyond, and we'll
Okay.
maybe delay the start of the next session by 10 minutes. I think that's
Okay,
what
well, let me try to be brief. So they have this model of how probabilities over hidden states are formed based on currently observed features, the model of retrieved context. This model is, in fact, has the same structure as the calculation of a Bayesian conditional expectation if you knew the correct joint probabilities, the joint probabilities of X and Y, the hidden state and the observed features implied by the generative model. So the only difference is how those estimated joint probabilities are formed. They have a rule for constructing over time these estimates based on memory of those joint probabilities. It's in fact, I think, a perfectly reasonable learning rule, assuming no storage constraint on memory, because it has the property that it would yield estimates that converge with probability 1 to the true probabilities if you were training this memory using correct probability assignments. In other words, if your mind were able to call up the correct conditional probabilities of hidden states when you see features, and you used that to train the memory process would indeed converge in the long run with probability 1 to the true probabilities, and hence the true then Bayesian conditional probabilities in the future. The reason it doesn't get there, even in the long run, is it's not being trained with correct probabilistic assignments. It's being trained with the subjective probability estimates that the brain is itself producing using the memory process. So the hitch is that they have to use these subjective associations rather than the correct conditional probabilities to be training the memory. And a question I have about this is, I can certainly see how it's a simple mechanism and doesn't require knowledge that you have to ask, well, where would the brain get the knowledge from? But it seems a little too solipsistic, and maybe I don't properly understand how it works. It seems to be a model that says that categories that the brain is inventing to interpret experience are forever reinforced simply because the brain has generated those associations before, with nothing checking this process to ask whether the categories are actually helping to make the world more predictable. And so that's at least a question about it. Jessica talked some about this, as saying how it could explain why associations of, say, stock market crashes with depression could persist a long time. And the question is whether the model isn't set up to make these things too persistent. There are many algorithms in the machine learning literature, for example, that studies the problem of algorithms that should do unsupervised category learning. Namely, you learn to categorize things without anyone telling you what the correct categories are. And that literature has come up with clever algorithms that can learn models of categorization where the categories will in fact be useful for prediction. I guess my question is, do we know from memory studies that the human brain doesn't work like one of these unsupervised learning algorithms? Or is it doing something cruder that gets more easily stuck on superstitious beliefs that persist forever? Finally, just to say a little bit about the second aspect in which the model is different from just straight Bayesian learning. There's this model of how the retrieved context then gets turned into a forecast. The estimated context is in general not just the retrieved context, but an average of these retrieved contexts over recent observations. They're averaged over a time window. The length of that time window is determined by this parameter zeta that you saw in Jessica's slides. The current estimated context is then furthermore assumed to persist to whatever future date that you're forecasting about. So the probability distribution over the features at that future date is the one generated from the current estimated context. So that's a simple heuristic which has some very sensible features. But unlike exact Bayesian inference, it doesn't require any knowledge of the parameters of the true generative model. That's the advantage of it, and that's what's perhaps very sensible about it. But I have a question. I mean, the results, and Jessica didn't talk too much about these, but there's a lot of discussion in the paper of how both underreaction and overreaction of beliefs to changes in the environment relative to the ideal Bayesian observer can result from their model. And these results depend a lot on assuming this arbitrary way in which the current retrieved context gets averaged over time and then extrapolated into the future in ways that are hardwired, that don't involve any parameters that are estimated off properties of the environment. And I guess the question about that is, are we sure that the cognitive processes people use are as little able to adapt to the statistics of the environment as is being assumed here? I think there's a lot of evidence that people and even other organisms like pigeons have a good deal of ability to recognize change points, recognize points in times when the statistics of their environment seem to have changed, and that what one observes is that beliefs seem to change more rapidly than simple averaging over a fixed time window at all times around these perceived change points. And in fact, I think it's the existence of phenomena like that that actually motivate a lot of the author's interest in having this model with the hidden states that can lead to, the sudden jump into the past that Jessica was talking about. But I wonder if this model where the length of the time window is simply fixed and is the same at all times, and the degree of extrapolation of the current context into the future is also the same at all times, is really consistent with what we observe about people's ability to respond to perceived change points and change the degree to which they're time averaging current beliefs with things they were thinking about in the past. as they perceive those. And I guess that's as far as I'll go. I think, this is a very rich framework. Both, it's fascinating, the connections with memory literature that Jessica didn't have time to talk much about, the many applications to puzzles about expectations in asset pricing contexts are also very intriguing. And it's a model that I think can be developed much further. I hope that as we get into this literature, that we do think much further about it.
Andrew, you're muted.
Yeah, thank you very much, Mike. I want to give Andrei and Jessica a moment to respond. We are certainly going to start the last session a little late at 3 o'clock. That's okay, we'll survive. So that means we can continue this discussion a little bit longer than we'd otherwise thought. So Andrei and Jessica, if you'd like to respond.
All
and then
good.
I see hands raised.
I'm all good. I understand the comments. I appreciate the comments. Mike is
right.
his usual
Thank you.
wonderful self. We'll address in due time.
Jessica.
Thanks so much for those great comments. I guess quickly, so I focused on this one case where like you have a completely solipsistic agent. But when you move away from that parameter configuration, which is actually not a realistic one, to the realistic parameter configuration, things become more complicated, but there's actually no way to stop the agent from learning. And so the agent learns just more slowly. Now we do know that there are situations in reality where agents don't learn, and you do have that problem. But I think the difference between the internally generated features and the external ones is that the internal ones are not persistent in the way that the external environment is, presumably. Not all of this is fleshed out in the paper. And so that's something that we should be clear about, though some of it is also, we know that for this model to work, sometimes the agent has to use external features and sometimes internal features. And this is something that in the memory literature is also not resolved. I guess the other point to Mike's comment is that we also know that there is such thing as like a conscious override. If you have an association that's clearly not appropriate, the agent can at some cost override it. And that's also a process that we don't know much about, but is interesting to explore. In terms of agents knowing that they're from going into a new environment, to some extent that's in there because a context, you can enter quickly into a context, different context, and your beliefs shift. That said, there are studies in memory that take that context evolution equation and exactly as Mike says, say that you should make it a little richer by having a time varying zeta. So the most like up-to-date models do have a time varying zeta, and sort of, I think actually a really interesting thing to look at is whether that time variation, how much of it's under conscious control. So if maybe that is if we think that this is producing underreaction, that would have the prediction that if you distract the agent, you would see something more like context evolution that we have, and otherwise you would see more of a conscious override. So anyway, thank you for your comments, and that was great, and we're gonna think carefully about them.
All right, that's wonderful. I'm looking now for questions and hands can be raised. Stefan, and do you see?
No, actually, I don't think there have been any questions so far, but whoever has one, please feel free to unmute themselves and just ask directly in person, I would suggest.
Well, we must have hit the bliss point. So people are very reluctant apparently to take us past the 250 ending. So we will accept. There is one point which I think I want to make to everybody, which is this is an area, the area of memory, that is clearly very exciting and expanding. And I think that among the various faculty-led groupings, I could easily imagine there being one in which people wish to take on memory, and the graduate students who find this exciting could join in possibly having, you know, the best leadership in the world of such sessions. So thank you very much. Most exciting.
Thank you.
Thanks.
We'll be back in 15, since I've now left some confusion about when the next thing starts. We will, in fact, take a slightly longer break and be back at 3, but I'll be here the entire time. And if everybody's here, we'll start. Thank you.
That sounds great.
Thank you. Wind, can you please send me your slides? I
Yes,
just wrote
yes,
you an email.
Yes, absolutely.
Thank you. Jessica, this is
Likewise.
great.
Oh,
Jessica, this is fantastic.
Yes, I also, I think this is an important development over the version I had read, you know, I forget if it was like a year ago, right? And, you know,
Yes,
I like
it's moving in a very good direction. Yes.
well, we've been thinking hard and about all the amazing comments that we've gotten. So, so I think it's been a great process, and yeah, thanks. Very appreciative for the comments and for the chance to present this new version here. That's been especially valuable.
That's kind of wonderful for us.
Thank you.